afternoon, everyone. I'm Kate Miller. I'm Head of Marketing here at Ecosulis. Welcome to the Nutrient Neutrality Solution webinar with our Innovation Lead, Sam Gandy. Sam's presentation will be about 30 to 45 minutes today. Sam will do his presentation, and then at the end, I'll just start picking the questions out and pose them to Sam for you. I think that's everything from me so far. I'm just going to hand over to Sam, and then I'll see you all for the questions at the end. Thank you.
Thank you, Kate. Yeah, so okay, just to kind of set the scene, I'm sure some of you may be aware of issues around nutrient neutrality, and I'm going to be looking at one potential solution for mitigating nutrient pollution. Before I go into that, just a very brief introduction about me, how I sort of got into this. So yeah, I have a background in ecology, have a PhD in ecological science, and I looked at soil restoration in Ethiopia. And then I've also worked for a year at the University of Leicester on ecological river restoration, and then sort of with Norfolk Rivers Ecology. And that sort of gave me some experience with these integrated constructed wetlands and their potential role, not just in mitigating nutrient pollution, but also enhancing biodiversity and providing a kind of multi functional range of benefits, actually. And this is how I sort of first approached Ecosulis, because I thought, this sort of aligns with the ethos of the work being done, and it's kind of seems like a good bang for your buck in terms of overall benefits. So yeah, here I am. So to touch on nutrient neutrality, I'm sure many of you listening to this are aware of the state of our waterways and our wetlands. They are imperiled by pollution from multiple forms, from agricultural runoff, from sewage. There's quite a lot of raw sewage that's entering our waterways in times of heavy rainfall and high flow. And this has had grave impacts on our waterways all throughout the UK. And according to sort of quite recent assessments a few years ago, every single waterway failed on its chemical status when assessed, and only 14% passed and were granted good ecological status by assessments by the Environment Agency. And this problem seems to be, if anything, getting worse. And so, yeah, Natural England sort of stated made a kind of a ruling and issued advice to try and do something to sort of prevent this kind of worsening situation with our waterways. And yeah, new rules, new regulations have come in where any change in land use, so things like property development in an area of a river catchment, a particular catchment area that has a site of conservation importance or interest. There are rules that will apply to that catchment where any land use change or development must be able to demonstrate that it's not going to add to existing nutrient pollution inputs entering waterways. And this is being sort of now, these rules are being kind of issued to about a quarter of all local planning authorities in the UK, and about 100,000 homes are on hold in terms of construction because of the bottlenecking here. So developers and councils have been sort of scratching their heads a little bit in terms of sort of wanting to know how to kind of move past this. What options are there on the table? And one potential option, and there are a few sort of different ones, is these so-called integrated constructed wetlands. there's a few different types of constructed wetlands, and so there's these what have been termed free surface water, free water surface, or free surface flow wetlands, that I'm going to kind of call here integrated constructed wetlands. In particular, that's a kind of, I guess, slightly more widely used name, but those names are all sort of denoting the function of the wetland, in the sense that the water is sort of flowing over the surface and being sort of treated that way. The other forms of wetland that are also used are horizontal subsurface flow and vertical flow wetlands, and these are sort of used in sort of more specific contexts, and they have different sort of engineering requirements. So they use beds of filtering material as well as things like vegetation, but they're sort of, yeah, they're quite sort of distinct from this specific type of wetland, the integrated constructed wetland. So yeah, some of the advantages. So why integrated constructed wetlands? What are they bringing to the table that, say, modern conventional mechanical sewage works, water treatment works, all these other forms of wetland are bringing? So a kind of important advantage over sewage works is their operation and running costs and maintenance costs. So they sort of tend to come out at sort of between 10 and 50% cheaper to run and maintain. They don't require any energy input if they're gravity fed. They can also, pumps can also be used, but in the right situation, they can be designed in such a way as they're being gravity fed, so there's no power requirements. They have sort of great design flexibility, hence the integrated part of the name. They can be plotted in and sort of individually engineered or tailored in a kind of bespoke way, depending on context. They're also more, once they're established, they're more tolerant of variation in flow and pollution loads as well. Yeah, that they can sort of take a little while for the vegetation to become established, but they can sort of take on periodical volumes of high flow, and then in some cases no flow at all. These particular wetlands, they support much higher biodiversity than conventional sewage works, as you might be unsurprised to hear, but also the other wetland types as well. They also provide public amenity and aesthetic value. And now I'll kind of touch on that more, whereas these other wetland types don't so much. They're sort of more kind of functional and filling a specific role. So yeah, just to sort of touch on some of the basic considerations when designing these wetlands. So of principal importance, before really any other considerations, is acquiring the necessary land area to construct the wetlands. And yeah, research has shown that the overall land area is kind of, that you give over to a wetland, is supportive of the nutrient pollution reductions and also the biodiversity enhancing potential. Well, another consideration, as I've already touched on, is gradient. So, you know, often these wetlands are constructed between, say, a sewage treatment works, wastewater treatment works, and the nearest kind of moving water body, river, that effluent discharge will be going into, and the wetland will be kind of plugged in between the sewage treatment effluent outflow and the waterway. And in the sort of optimal situation, there will be a kind of slight gradient And it doesn't need to be much. I think it's a centimetre for every metre, every 100 centimetres. And just that slight gradient then will allow the water to move through the wetland cells and then be treated. Another important consideration is soil type, and obviously soil porosity. You can't construct these wetlands in areas where you've got of infiltration and you're going to sort of lose the water. But there are potential ways around this, and some wetlands will be lined with bentonite clay, and so yeah, clay soil is optimal, and obviously this can be tested by taking some soil samples as part of the kind of feasibility assessment of constructing these wetlands. But yeah, Ecosulis, we've had an idea of maybe sort of you could incorporate a harder shell design to these wetlands, which would then allow you to sort of construct them in principle anywhere. Because one thing with a bentonite clay liner, eventually you're going to have to dredge and potentially maintain these wetlands. And if you ended up piercing the liner, that's going to be an expensive problem to amend. So just to give an overall function of how an ICW works. So as I've touched on, the wetland system, so it's usually a number of separate kind of wetland cells or ponds, and they are linked up together via pipes, and the level of these pipes can be adjusted easily, and that in turn adjusts the water levels of the wetland areas, and the water will then flow either through gravity flow or having been pumped through these different wetland cells, and it will then be processed in a number of different ways. So you've got a sort of a broad suite of different things happening. You've got the effects of sunlight and water and vegetation and microorganisms, and all these different sort of biotic, abiotic factors are sort of all having their own effects on the pollutants. And it should be emphasized that of all the wetland types, the ICW is most closely mimicking the ecological function of a natural wetland system, far more than the other wetland types. And it's also important to say that the overall treatment efficiency of these wetlands is greater than the other wetland types that I mentioned. They have their own particular strengths in terms of some of the pollutants that they target, such as phosphorus or certain forms of nitrogen, but these integrated constructed wetlands provide the greatest overall treatment efficiency. And so the water will move through these wetland cells and sort of be retained within them for some time before then sort of flowing back out into the waterway system, sort of having had time for those various aspects of that system to sort of process those pollutants. Yeah, sort of perhaps an unsurprising thing to learn, but the overall area of your wetland is a sort of primary predictor of treatment efficiency. So, and that's particularly relevant to phosphorus as well. And phosphorus is a more persistent pollutant than nitrogen-based pollution, because as part of the nitrogen cycle, you've got denitrification. Nitrogen gas will just go out back into the atmosphere, and that doesn't happen with phosphorus. So yeah, that's an important kind of thing to consider here in terms of pollution mitigation. So this is a figure depicting the overall nitrogen and phosphorus. So the total nitrogen and the total phosphorus concentration reduction associated with various individual ICWs. And so the figure, the bars on the right of the figure here that you can see, that's the mean of a number of different ICWs taken from a review paper, which I should note is 20 years old now, and there's been sort of more constructed in that time, and sort of better knowledge gained about how to increase efficiency. I should point out that the middle bars on the chart here, Glasgow ICW in Ireland, this is a sort of a special case in the sense that this is treating farmyard effluent from a dairy farm in situ, and that's unusual. And I should say that often ICWs are used as a tertiary or polishing treatment step. So this is why they're ideally situated by a sewage treatment or water treatment works that's done the sort of some of the primary and secondary processing of the water in terms of and treating the pollution. So these wetlands are sort of ideally designed for kind of like high flow, relatively low pollution inputs. But as you can see here, they kind of show quite sort of, well, it's quite variable, but sort of fairly robust levels of nutrient reduction. And there's considerations in terms of design where you can kind of maximize the potential nutrient reduction capacity. So the dimensions of the wetland cells and the total area and factors like this can influence macrophytes and plants as well, can all sort of help reduce the overall nutrient load. It's important to emphasize here, so one of the potential positives to come out of the nutrient neutrality is the generation, or the potential for generating nutrient neutrality credits. So where it's sort of can be demonstrated that there's a mitigation in nutrient pollution of phosphorus, of nitrogen, this can sort of generate credits, and these credits can be traded within an impacted catchment. So as I mentioned earlier, any catchment that harbours a site of conservation interest is likely to sort of be affected by nutrient neutrality regulations. But one of the flexible rules here is that non-affected areas of that catchment can do their own nutrient neutrality mitigation and then trade credits, say with developers or other people that are being stopped from developing or progressing with whatever projects they've got. And there's the potential here for other credits to potentially be stacked. So there's the nutrient neutrality credits, nitrate credits, both sort of falling under the banner of Natural England. There's also phosphate credits as well, and that's a DEFRA initiative. So there's sort of potential, for stacking here. Obviously, some people here will be familiar with biodiversity net gain, an ever recent kind of crediting system that's come in to try and facilitate biodiversity enhancement. And having spoke to Natural England briefly about this, it's not quite as simple as being able to kind of stack BNG credits onto nutrient neutrality credits here. For one thing, given the current quite sort of rigid rules regarding BNG, even though these wetlands can provide biodiversity uplift, as I'll touch on, and habitat creation and things like this, under current designation, these wetlands are likely to fail on water quality status, unfortunately, at least sort of early on in the wetland treatment cells. So a big part of our work at Ecosulis, big passion is biodiversity enhancement and habitat creation. And this is principally why my interest was first kindled in these wetlands. Obviously, they're functional. They're serving a purpose. They're a form of organic technology for treating water pollution. But there's much more to them than that. And there's a sort of growing body of research to show that they can benefit biodiversity in different ways. So one study looking at macroinvertebrate diversity in a 5-cell ICW system found that as you sort of progressed through the wetland cell treatment chain, as you got to the later cells in that wetland system, the macroinvertebrate biodiversity sort of went up, as you'd kind of expect from the improvement in water quality. And it was found that overall contribution to biodiversity, macroinverted biodiversity at a catchment scale was high. Another study found that in Ireland that an ICW systems there supported a quarter of all known water beetle taxa in Ireland. And that's important because macroinvertebrates and water beetles are used as bioindicator groups. They're a useful group to assess, because if you've got sort of high biodiversity of these groups and high functional diversity of these groups, it's a fairly good and reliable indicator of overall ecosystem functioning and health. There's another study looking at ICWs in Norfolk, and that found that the number of species of birds following the construction and establishment of these wetlands went up from 10 species to 27, and this was a fairly modestly sized ICW system as well. I visited it actually, and it also harbours a thriving colony of water voles, and otters visit it as well. So these wetland systems in the right areas can potentially support species of conservation value. And I'd also ask us now maybe to kind of zoom out a bit and have a kind of landscape lens view of these wetlands. We've lost up to 90% of our wetland habitat in this country, and wetland habitats are incredibly rich. Although they only cover about 1 to 2% of the Earth's surface, they harbour about 12% of all biodiversity. They're kind of lifeblood of the larger landscape. And so given that we've lost so much of it, if we have these wetlands back and it's sort of constructed at sufficient scale in the landscape, they could provide these ecological stepping stones in the landscape. And I appreciate some people listening to this might be in some sense rewilding or habitat creation purists. You know, they feel like, well, you know, it's going to be a degraded substandard form of habitat, but I don't think it's as black and white as that. And I feel that the more of these wetlands we have at scale in the landscape, it's going to have kind of like broad scale benefits to biodiversity, given the sorry state of the water quality of our waterways and the just lack of wetland habitat. And given our sort of passion for biodiversity enhancement and habitat creation, it's also possible to design these wetlands in such a way that you can maximize the biodiversity value of them. So one thing to consider is the number of wetland cells, and it seems like a minimum number of 4 to 5 can be beneficial. And because if you build more wetland cells overall than say fewer large ones, you're going to get more of a gradient then of water quality. And it's important to emphasize as well that the first cell in a wetland system will tend to do quite a lot of the heavy lifting in terms of the sedimentation that will be settling in there. So yeah, the number of wetland cells, also the wetland cell dimensions. One study found that roughly a 1:2 ratio of width to length seemed sort of reliable for overall efficiency and biodiversity supporting potential. But there's additional ways of potentially enhancing biodiversity as well. So when these wetlands sites are constructed, you're going to generate a lot of spoil from excavating them. And a nice thing about this is that because it will be subsoil, it will be nutrient poor, and you can potentially do some landscaping with that, and then sow that with local Providence wildflower seeds. And obviously wildflowers prefer lower nutrient soils. You can potentially plant some native trees as well. And also, for not much extra cost, you can potentially excavate a few ponds adjacent to the cells. So there's potential ways that the biodiversity supporting potential of these areas can be further bolstered. Yeah, to kind of follow on, I guess, from the concept of these wetlands potentially functioning as ecological stepping stones, we also need to think again as their potential as a kind of integrated ecological environmental approach at scale. Given how imperiled our rivers are from sort of the effluent that they're sort of taking on and the nutrient load, if we had sufficient numbers of these wetlands, it could help take some of the pressure off our ailing waterways. And obviously, there's other kind of inputs going on in terms of more diffuse agricultural runoff. But if these wetlands were constructed where you've in the appropriate places where you've got sewage treatment or wastewater treatment works going into rivers, it could potentially have wider ecological benefits beyond the wetlands themselves. And it's important to note that it's been estimated that around 75% of marine rewilding initiatives focusing on a single species fail. So, and these aren't a magic bullet solution. I see them as kind of like one option or kind of one tool in the box, to put it crudely. And other things like beaver reintroduction, there's good scientific data now to show that beaver damming by trapping sediment, they can also reduce nutrient and phosphorus loads from going further downstream, and then that sediment will be colonized by vegetation, much like these engineered wetlands. And as well, the implementation of buffer strips around waterways as well. So we shouldn't be farming up to the edge of our waterway. We should be sort of giving a bit more space and a bit more breathing room. In Bavaria, for example, they tend to implement between 10 to 20 meter buffer strips between waterways and farmland, and this works really well as to sort of buffer the effects of beaver eco-engineering as well. So it's like a sort of two birds with one stone kind of approach. So yeah, these are just one option of several that can potentially be implemented at scale for benefits to both nutrient pollution mitigation, but also biodiversity uplift as well. There's other benefits as well to the ICWs, and yeah, just to kind of touch on some of the other pollutants that they can remove. So obviously nitrates and phosphates aren't the only these kind of entering the waterways as a result of human activity, but these wetland systems have been found also to be effective, and in some cases more effective than conventional water treatment works in processing things like biocides and steroidal hormones, pharmaceuticals, pesticides, petroleum derivatives, coliform bacteria, bacterial antibiotic resistance genes, heavy metals, and microplastics. And many of these things will be broken down in situ. Heavy metals, they're more likely to be kind of sequestered in perhaps the first wetland cell, which will kind of require later testing perhaps. But yeah, it seems like these wetland systems provide a much wider bandwidth of pollution control than your more conventional wetland systems treating sewage and pollution. Another important aspect as well is these wetlands, because they're visually appealing. I mean, they sort of to a large extent resemble natural wetlands. They don't tend to smell or anything like that, and they can provide public amenity value. And this can potentially be enhanced, with, say, public footpaths sort of nearby, provision of like benches, maybe kind of notice boards to provide a bit of information. And there's potential sort of educational research value that can come from them as well. There's a growing body of evidence to show that, contact with natural settings, in particular, wetlands, so-called blue spaces, and obviously these are a kind of mosaic of green and blue spaces, can be beneficial to our mental health. One thing actually that I've maybe not touched on too much is, well, I mentioned that the maintenance costs of these wetlands and needs of these wetlands is much less than your average conventional treatment work, but it would be a mistake to say they are maintenance free. You can't construct these wetlands and then sort of walk away, job done, and sort of brush your hands of it. There's a few things that need to happen. It's often not particularly kind of intensive, and it will be kind of periodical intensive management and then sort of hands off again. But they will require kind of monthly checks, at least. Some people recommend weekly, and this is just to kind of keep an eye on the wetland functioning, on the water levels, particularly as it's becoming established. And there will be inflow pipes connecting the various wetland cells, and they will just need occasional checking just to make sure they're not blocked. The verges around the wetland cells will need mowing occasionally. You don't want scrub encroachment because that's going to drop organic matter and leaves into the wetland cells, and that's going to kind of speed up the natural sedimentation process that will be occurring. So an important consideration is to leave ample room that heavy machinery can access all sides of your wetland cells, not just for doing the mowing, but also actually accessing the wetland cells themselves. Yeah, there's certain practices as well. If biodiversity provision is an important consideration, as we think it is, certain management practices can be implemented to kind of enhance the biodiversity value of the site. So having a mix of open water and also emergent vegetation and submerged vegetation is likely to provide a range of different microhabitats and niches, and will uplift the biodiversity potential. Longer term, after say maybe 10 to 15 years, the wetland cells will require dredging. And one nice thing about the flexibility of these systems is that you can take one cell offline and sort of then potentially kind of redirect it to one of the existing cells. And this material will require dredging, and that will essentially reset the cell. I mean, there might need to be some replanting of things after that time frame, but as long as you're able to do that, these wetland systems can kind of essentially function indefinitely. And following the dredging of the wetland cells, having looked into this in terms of what becomes then of the spoil of the sediment, there's no sort of like single process. It requires a bit of a bespoke approach as to the kind of disposal of this spoil. So it's likely to require some chemical analysis to make sure it's not contaminated with heavy metals or other things. But the common destiny for the spoil that's excavated from these cells is use as an organic amendment on fields. Thank you. That sort of wraps it up.
That's fab. Thank you so much, Sam, and thank you all for your questions and comments. There's been absolutely loads coming through. It's been quite tricky to stay on track of them all. Thank you to Chris just for answering a lot of those as we've kind of gone along. I'm just going to go through and pick out a few. We've still got quite a bit of time left, so I'll go through and pick out a few for you to answer, Sam, if that's okay.
Okay.
So the first I have is from Chris Farmer. I presume these only function correctly when they are outside the river's functional floodplain.
Yes, no, that's a good a good point. So part of the feasibility assessment will be kind of assessing the flood risk zones and ensuring that they're sort of sufficiently elevated that they're not going to be at risk of being inundated by any nearby rivers or waterways. Yeah, that's an important consideration.
Thank you. The next question is from Victoria Chester. Are those other types the horizontal subsurface flow and vertical flow systems you were talking about? What specific pollutant are these better for?
So I can't remember which one it is, but one of those types is more efficient at treating phosphorus in particular, I think. Whereas, and they have a higher efficiency in terms of the area that they take up in terms of the overall nutrient processing. However, they're sort of more adept at processing some forms of nitrogen than others, and they'll be less good at dealing with some other forms of like ammonia and things like that. So they're more specific in the forms of nitrogen and forms of phosphorus that they treat, whereas these free surface flow wetlands provide the greatest overall treatment efficiency for the different forms of nitrogen and phosphorus that you get as pollution.
Thanks, Sam. A question from John. Is there a significant seasonal variation on the removal of N and P?
Yes, there is. So yeah, during the summer, you're going to get I think overall the phosphorus levels tend to be mitigated more when you've obviously got more active plant growth going on, and then there is a sort of a bit of a dip, I think, towards the winter months. And I should say actually one point I sort of was meaning to mention but didn't is that it has been shown that after a certain amount of years of functioning, the phosphorus removal efficiency can go down a little bit in some of the wetlands. But there was one study that looked at sort of performance after 10 years, and it took sort of an average nutrient removal efficiency, and it found that even after 10 years, 53% of total nitrogen and 67% of total phosphorus was still being removed by the wetland cells.
Thank you, Sam. Another question from Victoria Chester, and a comment as well. So, not sure I like the idea of stacking credits. Sounds like it's a bit of a get out clause to me. Are there limits or particularly sensitive areas that cannot be credited against?
Honestly, I don't know. I'm not altogether sure on the sort of the implications of the credit stacking, if I'm honest.
That's okay. I'm sure we can delve into that for you, Victoria, and get something across to you kind of later today. I think that's a question I think a lot of people do kind of ask when it relates to credits. I think there's lots of divided opinion around that as well. So we'll have a little look for you and we'll see what we can find out. Another question from John. Is chemical testing the only reliable way of evaluating the efficiency of nutrient removal, or are there accepted protocols to evaluate based on flora?
I think to sort of demonstrate nutrient pollution removal efficiency, it has to be via chemical testing. There were a few different ways of doing that, and you can get sort of like home kits and things like this. Some of these wetland systems, they build in sort of ways of detection apparatus into the actual design, so they can kind of monitor the sort of the influx and then the outflux of the pollution levels. But yeah, I think to sort of cover yourself, you need to be taking the chemical assessments. You can't just rely on, say, indicator organisms. You've got to back yourself up with chemical data.
Another question from Victoria: is there a minimum or maximum size of cells/sites?
Is there a minimum size? Sorry,
Minimum or maximum size, yes.
So this is one of the interesting things about these wetland systems is the design flexibility. So they can literally range from a few square meters to a few square kilometers, and anything in between. And that obviously will, they can be designed purely based on the needs of the specific context, but they can be hugely variable in size.
Thanks, Sam. Question from Victoria: have you got some good recent examples of ICWs used, one as a replacement sewage works and two in conjunction downstream from sewage works, preferably in a fairly urban area?
You know what? Not off the top of my head, in the sense that at least these specific types of wetlands, they're more well suited to kind of local, relatively localized population centers, so not sort of large kind of urban centers so much. I mean, there are large wetland systems in other parts of the world adjacent to large urban areas, but these tend to be kind of serving kind of, towns, villages in more kind of rural situations. I mean, I think there's some good data in Ireland of ICWs there, where they're used rather than sort of as a supplement to wastewater treatment. They're kind of used as standalone ways of reducing nutrient pollution, and they can do that. But I think the specific example in Ireland I'm thinking of, which had amazing removal efficiency. I think over 99% of phosphorus and 95% of nitrogen were removed, which obviously is pretty impressive. The quality of the water leaving that ICW was as good or often better than the baseline water quality in the river itself, which is both kind of hopeful and also depressing. But yeah, there's not going to be much data apart from that case study and maybe a few others on their efficiency as standalone interventions for this specific type of wetland anyway, because they're more designed for the tertiary or polishing stage of water purification. The other wetland types that I mentioned, they are better at handling sort of secondary processing of effluent, but that requires extra engineering capability to accommodate that.
Thanks for that detail, Sam. Question from Cara: how easy are the ICWs to maintain? Do they need to be excavated every few years, and do the reeds need cutting yearly? If they need excavating every few years, how can you support the biodiversity within the wetlands during this time?
So as I touched on, it will vary obviously with an individual context, but you're looking at about 10 to 15, maybe even up to 20, but around 10 to 15 year cycle of dredging. And obviously, you've got to sort of mow the embankments to prevent scrub encroachment. There are variations in how they're managed. So some people do strim the phragmites, the reeds that often make up these systems, and that could be a yearly or bi-yearly management system. Yeah, and then obviously the checking on the inlets as well. But relatively speaking, the overall management requirements are sort of less costly than, say, a conventional treatment work.
So do you have studies showing the levels of pollution reduction going through the various cells over the various stages of the ICWs? When do the cells become safe?
I'm sure. So not off the top of my head do I have data for the pollution levels across the different cells. I'm sure there'll be studies that have taken that into account. At least some of the studies I've encountered simply do a before and after. It might have been looked at, but it's not something that I've come across in my research. But yeah, the later cells, I mean, I'd be careful about using the word, well, like safe. Sort of, yeah, the later cells in a treatment system, the water quality will improve, and that will be kind of reflected by the macroinvertebrate community and sort of the indicator groups there. But again, it's these, you know, it's an individual kind of bespoke type deal, so it's hard to sometimes make generalizations depending on the inputs.
Thanks, Sam. And just to follow up as well from Victoria on that. So how do you design the ICWs to work alongside downstream of sewage works?
Optimally, so you know, usually you'll have your sewage works or your waste treatment works, and that will the kind of the sewage will have been processed, you know, primary, secondary processing in there, and then you'll have a kind of like the outflow pipe will will go into the nearest waterway, the nearest river. And so essentially when you're constructing and these wetlands, you're essentially kind of, to put it crudely, like chopping off that pipe and plugging in the wetland to the end of the pipe coming out of the sewage treatment works. So it's then acting as a kind of buffer between the sewage works and the nearest waterway. And optimally, you'll have a slight gradient between the sewage treatment works and the nearest waterway. And that can also be accounted for in the design and the construction and the excavation. Obviously, you don't want to be like excavating hundreds of tons of, or like, you know, to sort of engineer a gradient, but you can engineer a gradient to some degree, but hopefully you'll have one to already work with, and that the gravity then will take that effluent from the sewage treatment works and run it through these wetland cells, and then out the other end after a certain time of residing within the cells and going through the various treatment processes that are active there.
Thanks, Sam. Question from Eloise. Could these be integrated near outlets for combined sewer systems to mitigate the raw sewage there?
Yes, potentially, but not so much with the raw sewage. And as mentioned, they're not, these particular types of wetland are not geared towards processing untreated, unprocessed sewage effluent. There is isolated case studies of them being used to process, you know, raw farmyard, dairy farm effluent and waste. But for the most part, these require or really benefit from some level of prior processing before they then accommodate that water to treat it. So they're not so much geared towards the raw sewage.
Okay, thanks, Sam. I'm not sure if you'll be able to provide these or not, but I think it's quite a good question, so I'll ask. From Siobhan, are there any good examples of ICW successfully installed in areas with existing public access, and how this was managed for safety amenity?
Yes, no, there are a number of cases. So there's some case studies in Norfolk, so the Ingall wetland there. There's a few others, and yeah, I did some feasibility assessments for ICWs for Wiltshire with Wessex Water, and in those cases there were kind of existing public footpaths, but then extra kind of amenity potential was provided by benches and information boards like that. I mean, these wetlands are pretty shallow for the most part. I mean, they only have a sort of depth of water between 10 and 20 centimeters, maximum 30. And that sort of is optimal for nutrient processing or nutrient pollution mitigation, but also it happens to be that, yeah, shallower water bodies tend to be richer for biodiversity overall as well. So it's kind of like, yeah, an added benefit there. So yeah, there's kind of there's not too great a risk in terms of falling into them, because they tend to be quite shallow and they have sloping sides. It's more of an issue of like, dogs might jump into them and things like that. But yeah, having visited one, I didn't feel like there was much kind of risk there in terms of, and yeah, we'll tend to have clearly delineated public footpaths and things like that.
Thanks, Sam. We've got a couple of minutes left, so I'll just ask one more question. Apologies to those that I haven't come to, as they do just keep coming as you're answering them, Sam, which is great. So if we can answer any kind of post-webinar, we will do so. So the final question for today is from Matthew. Should ICWs only be used to catch high flow discharges, and also only be developed in tandem with increasing capacity at treatment works?
I think that's optimal, yeah. So they are good at coping with high flow and also variations in flow. As I mentioned, they can once the plants community is established, they can take on board high volume flow, and also at times of even no flow. So they have more inherent flexibility there than conventional works. And yeah, but I guess their optimal application is when they're kind of working in tandem, I would say, with existing or potentially upgraded waste treatment or sewage treatment works.
Brilliant. Thanks,
rather
Sam.
than a standalone. Yeah.
Great. Thank you very much. Yeah, thank you all for your questions and comments. There's been some really great conversations, I think, happening on the chat as well today with a few people, and thanks to Chris as well for feeding into some of those answers as well. As I mentioned earlier, we have recorded the session today, and I'll send this out to you all. It's likely to be Monday morning now, but in the interim, if you have any questions, please do just drop us an email, or do feel free to connect with any of us on LinkedIn as well. It's been great to kind of host you all today, and again, thank you all for your questions. They've been great, and thanks to Sam and Chris as well. Thanks everybody, and have a fantastic weekend.
Thanks.